In 1965, Atlas Centaur achieved one of its major goals, completion of research and development for the single-burn lunar mission. The next single-burn flight will be operational, using vehicle AC-10. Emphasis in development shifted to support the two-burn Centaur, with the next R&D mission of this type assigned to flight vehicle AC-8. The most significant event of the year was the flight of AC-6, which occurred on August 11th. The final R&D flight test of the single-burn Centaur was a full-dress rehearsal for the first operational flight, which will place a surveyor spacecraft into a trajectory for soft landing on the moon in mid-1966. The countdown simulated an operational mission, with liftoff to occur within a limited time period referred to as the window or launch opportunity. For AC-6, the target was not the moon itself, but a point in space 240,000 statute miles from the Earth. For the single-burn lunar mission, 3 points must all lie within the trajectory plane: the center of the Earth, the point of launch, and the position at which the moon will be when surveyor reaches it. For Cape Kennedy, these conditions exist for only a few days of each month and for a time within each day, which may be only a few minutes or up to about an hour. 11 August 1965. Range is ready. Scheduled launch time, 9:31 a.m. or within 58 minutes thereafter, to begin a 63-hour surveyor flight to the paper moon.
Check propellant. Go 30 seconds. Pressurization. Go Atlas. Go Centaur. Hydraulics. Go. Guidance. Go. Spacecraft. Go. Launch director. Go. All recorders are fast. Initiating engine start. Last 10. Release. We have roll program in.
AC-6 lifted from the pad 4 seconds after 9:31. For 15 seconds, the vehicle rose vertically as the Atlas flight control rolled it to the proper flight alignment, which for this mission was 108 degrees from true north.
Roll program out. Pitch program in on time. Secure out systems.
At about 900 feet, AC-6 began a programmed pitch maneuver that placed it into a shallow flight angle. It reached Mach 1 at about 1 minute into the flight.
We show a nice, smooth attitude control. At this time, chamber pressures are good. Tank pressures are very good. He is good.
Aerodynamic forces increased with acceleration, reaching a maximum at 76 seconds.
Very, very smooth attitude control. At this time, we show a nice set of chamber pressures and a very smooth transition through Mach 1 max Q.
The first stage of flight continued until Centaur's guidance system sensed an acceleration of 5.7 Gs. A signal to the Atlas programmer triggered booster engine cutoff and jettison.
Atlas, we have booster engine cutoff. Atlas booster engine jettison. We show jettison.
8 seconds later, inertial guidance computed flight path error and sent correction commands to the Atlas flight control. At 171 seconds, the Atlas programmer initiated jettisoning of the insulation panels.
Centaur insulation panel jettison, all 4 panels. Panel jettison confirmed at AE.
25 seconds later, nose fairing jettison.
A nice, smooth sustainer chamber pressure.
Centaur nose fairing jettison.
We have fairing jettison confirmed at AE.
Shortly after, the Atlas programmer starts Centaur's propellant pumps.
We show boost pump start. We have boost pump start.
At 234 seconds, it switches on the Centaur programmer, signals sustainer engine cutoff.
We have sustainer shutdown. We have HACL. Close vent valve.
Centaur vent valves close, tank pressures are raised to engine start levels, a shaped charge severs the adapter between Atlas and Centaur, and the Atlas retro rockets fire to widen the separation gap. For about 5 seconds, Centaur coasts. Then its main engines ignite, beginning the powered flight of the liquid hydrogen vehicle. The direct ascent flight of AC-6 called for an engine burn time of 432 seconds. Actual burn time was 436.5 seconds. Powered flight ended 11.5 minutes after launch. Centaur coasted 69 seconds. Then Surveyor separated to continue the 63-hour flight to the target. 5 seconds after separation, Centaur's inertial guidance system instructed Centaur's attitude rockets to turn the vehicle around in flight. 5 minutes later, engine valves opened and unused propellants began to gas out through the thrust chambers. The small reverse thrust continued for 16.5 minutes, enough to widen the gap between Centaur and Surveyor 5 hours later to a distance of about 1,000 statute miles. Surveyor maintains its orientation in space by reference to the star Canopus. If the Centaur were allowed to trail along behind the spacecraft, Surveyor's star seeker might inadvertently lock on to the reflecting body. Separation distance must be at least 209 miles. The paper moon target was based on the moon's actual position for September 28th. The simulated target would have been at this point, near the moon's equator. Surveyor SD-2, if no mid-course correction were used, would have landed at this point. It would have taken only a minor mid-course correction to hit the intended target. Since this was only an imaginary moon, Surveyor passed on through to go into the most highly eccentric orbit ever obtained, with an apogee of 441,765 nautical miles, a perigee of 90.5. The spent Centaur went into orbit 93.3 nautical miles out to 243,277. The two vehicles will remain in orbit indefinitely. 10 days after the flight, the destroyer USS DuPont picked up one of the insulation panels jettisoned from AC-6 at a point in the Atlantic 500 miles northeast of Cape Kennedy. Although the panel was a bit weathered from 10 days in the water, analysis at Convair showed little charring from heat, from either ascent or descent. The separation charges had cleanly cut all edges. AC-7 is a sister ship to AC-6. In July, it was undergoing integrated tests at NASA's Combined Systems Test Facility near Convair in San Diego. The Surveyor spacecraft for AC-7 integration was a test vehicle, T-21, which simulated the flight version. In this Pathfinder program, engineers from Hughes Aircraft assembled and tested the model prior to installation. The control center at this facility matches the launch equipment at Cape Kennedy. AC-7 was the first combined vehicle tested here, inaugurating use of the new NASA complex. From this point, flight vehicles moved to Cape Kennedy to be readied for flight. First milestone in preparation was erection of the Atlas booster into the tower. Subsequent tasks included checkout of Atlas connections and systems and checkout of the recently refurbished complex. Build-up continued with installation of the Centaur adapter. Technicians hoisted the high-energy Centaur stage into position on September 17th. The flight of AC-7 was originally scheduled for late '65. Additional ground testing of the SC-1 Surveyor vehicle has resulted in a rescheduling of the first operational Surveyor flight. With the first phase of Centaur research complete, development activities focused on the second phase, refinement of the two-burn Centaur. AC-8 is the vehicle which will continue the development initiated with AC-4, which flew in December 1964. It will go into an orbit 90 nautical miles high before engine cutoff. It will then coast for 24 minutes, after which the Centaur main engines will restart to thrust a dynamic surveyor model into a simulated lunar transfer trajectory. Length of the second burn will be based upon velocity required rather than on a fixed time, as in the flight of AC-4. AC-8 is extensively instrumented. One of the measurements to be taken in flight will be tank skin temperatures during the full duration of the mission. These tiny transducers convert temperatures to electric impulses which are transmitted to ground stations via telemetry. There are 4 rows of them located 90 degrees apart around the tank. To accommodate the greater number of information bits required from a research and development flight, AC-8 will carry 3 telemetry units instead of the 1 assigned to operational vehicles. The 3 telepacks are capable of transmitting 54 information channels. 24 of them are commutated. The commutators provide a good example of the precision that goes into space components. Here, a number of these units are being preconditioned. Preconditioning is one of the requirements for electronic components. Each must undergo a break-in period specified for a particular unit. The commutators, after a functional checkout, go through a 50-hour run. During this time, the technician records motor speed and response for possible variations beyond stringent tolerances. A typical unit supplies the output for 4 channels of information. Each channel has a rotating pickup that alternately contacts each of the terminals on the central core. There may be as many as 28 of these terminals, each connected to one of the instruments mounted on the vehicle. The speed of the rotating pickup is variable. By this means, a single channel can carry up to 28 different information bits, repeated each time the pickup rotates past the terminals. For the AC-8 flight, telemetry will transmit 122 measurements from Atlas, 465 from the Centaur stage, for a total of 587 measurements to ground stations. Telemetry data will be transmitted by a single antenna. To accommodate the additional channels, the antenna has been modified by incorporating a 5-channel multi-coupler. Precision tracking calls for the addition of an Azusa tracking system. Centaur will be tracked by means of an antenna mounted on the vehicle. A second Azusa antenna is mounted on the interstage adapter to facilitate tracking of the Atlas booster. One of the major changes to AC-8 is the addition of a balanced thrust vent system. It is located at the forward bulkhead of the liquid hydrogen tank. 2 vent valves release gaseous hydrogen overpressures into a torus ring, which distributes this venting gas evenly to vent ports. The object is to ensure that even a small amount of thrust on one side of the vehicle is balanced by the thrust flowing through the opposite port, thus preventing spin-up of the vehicle during the coast phases. All of the components of this system will be subjected to an extensive test program. Tests began at the Sycamore Canyon Liquid Hydrogen Test Site with an evaluation of the modified vent valve. Before and after tests of the valve, engineers calibrate the poppet tension to determine if there has been any degradation in performance. The spring-loaded poppet is forced open by a hydraulic ram. A micrometer measures the distance through which it travels. This distance is also recorded on the x-axis of the oscillograph recorder. The y-axis records the amount of force required to open the valve to a particular position. Possible degradation is determined by comparing the before and after charts. Improvements include changes to the controller, solenoid, and addition of a means by which the friction between the poppet and its support post can be adjusted. Tests of the valve subjected it to a variety of operating conditions. On this test rig, the valve operated under a continuous high rate of flow, subjected to maximum stresses in the open position. At a second test stand, engineers programmed a cyclic endurance test. The valve was scheduled to operate for 150 hours. Tests revealed the need for a redesign of the adjustable friction post. Further testing was postponed until this could be accomplished. AC-8 represents the first use of the Pratt & Whitney RL10 A3-3 engine. Aside from this, there are two other significant differences. Helium storage is larger to provide pressurization gas for the two-burn flight. Also, there has been a redesign of the hydrogen peroxide system. Hydrogen peroxide is the propellant for 6 of the subsystems on Centaur. Liquid hydrogen boost pump, liquid oxygen boost pump, the attitude control cluster engines, the 50-pound thrust attitude control engines, and the new 3-pound thrusters which operate during coast flight to keep propellants at the aft end of the tanks. The system which feeds the hydrogen peroxide to using units is a modified design, making it necessary to run a series of tests prior to flight. These will be conducted in a special test stand at Point Loma. The supply bottle, under pressure, feeds peroxide to the manifold which leads past each of the operating units. Each unit operates independently, controlled by a solenoid valve. In flight, hydrogen peroxide jets will fire in a random pattern as commanded by the guidance system. For the tests, units will fire as commanded by a unique control instrument which resembles a player piano. The paper rolls past a row of photocells which sense changes in contrast from light to black. The first square activates the solenoid of a particular unit. A second pattern shuts it off. These on-off patterns will simulate the sequence in which booster pumps and attitude control engines might fire in flight. Inside the Centaur liquid hydrogen tank, there are two assemblies, which were the subjects of a special vibration test. They are baffles, which inhibit propellant sloshing in flight, and a structure known as the Christmas tree, which is the supporting structure for fuel sensors. Tests at Convair's dynamic test tower investigated the effect of engine vibrations on the lightweight structure. Instrumentation for the tests included closed-circuit television looking into the tank during runs. Accelerometers measured the amount of vibration transmitted to the interior structures. The tank was soft-mounted, suspended by pneumatic cushions. Initial runs used heavy-duty vibrators attached to the two engine gimbal mounts. In preliminary runs, these vibrated the tank over a range of frequencies from 10 to 300 cycles per second at a rate of 2 minutes per octave. On the first run, tank pressures were at handling levels. Vibrations were then repeated with tanks at flight pressures. The final series subjected the vehicle to random vibrations. In Phase 2, technicians installed the Centaur insulation panels for a series of lateral vibrations simulating engine start at launch. Two smaller 1,200-pound vibrators provide the shake frequencies. These were mounted in the tower at 2 different levels. The program of lateral vibration will be similar to that imposed on the tank during longitudinal shake tests. The design of AC-8's -3 engine incorporates changes that will give improved reliability, efficiency, and maintainability. These changes have increased length and diameter of the thrust chambers with an increase in weight of about 9 pounds. Convair is in the process of running an extensive test program on this propulsion system at Sycamore Canyon, Stand 4 near the Kearney Mesa plant in San Diego. Preliminary firings were completed with the -1 engine to determine the characteristics of engine sequencing and support equipment. Centaur's engines ignite in the vacuum of space. Ground tests, then, must provide a low-pressure environment for engine starts. At Sycamore, engine exhaust passes through large diffusers, one for each chamber. Before ignition, these are evacuated by means of a high-velocity steam system. For tests with the advanced Dash 3 engine, it was necessary to modify the diffusers to accommodate the longer and wider thrust chambers. The diffuser is essentially a tube which converges to a narrow choke near its center section, then expands slightly down to the flame exit. Installation of the new Dash 3 engines was a major task with an impact on many of the sight systems. Concurrently, technicians installed and calibrated test stand instruments, linking them to recorders in the blockhouse. For current tests, the liquid helium engine component chill-down system was installed near the liquid hydrogen boost pump. Liquid helium, the coldest known fluid, will flow to the engine to chill it before engine start. Chilling of components between the engine and fuel tank is done with liquid hydrogen. One of the unique features of the Sycamore test stand is its television capability. This includes 4 camera mounts, which provide a means of looking inside the propellant tanks during any phase of testing. This camera looks through a port into the liquid oxygen tank. A similar camera position observes liquid hydrogen levels at a point near the level of depletion. A third camera watches the duct through which liquid hydrogen flows back into the tank during recirculation. A fourth is on the forward door, looking down at the surface of the liquid hydrogen fuel. Test engineers can observe the behavior of propellants at all times, or record the display from one or more of the cameras by means of videotape recording, or photograph selected action during a test with motion picture cameras. Photographic instrumentation also includes high-speed cameras which encircle the test stand. The most significant product of testing is information. At Sycamore, it is recorded by several different means. The Sycamore blockhouse contains a versatile array of recording devices. These information recorders include 160 channels, similar to 160 stopwatches which record the exact time of any selected test event. Centaur testing uses 111 channels. The oscillographs are used primarily to record quantities, such as measurements of temperature, pressure, flow, and so forth. There are 2 banks of oscillographs capable of recording as many as 89 parameters simultaneously. Centaur uses 72 of these during firings. There are 111 information points on the test vehicle which feed through a portable telemetry cart. The Taco cart houses flight telemetry packages which condition the signals. These are transmitted by radio link to the blockhouse. Telemetry is recorded on 14-channel tapes. Some of these are recorded directly onto Sanborn recorders or onto a 10-channel CEC. The CEC tracks provide a quick reference to commutated data samples. FM tapes record an additional 63 of the information channels. For evaluation, data on these tapes will be transferred to graph form after a test. Block 2 of the test program got underway in November with 2 cold flow tests. In these, runtime is a 5-second pre-start, followed by a 5-second propulsion flow. The first cold flow investigated conditions preceding the first burn of the 2-burn mission. The second cold flow simulated second burn conditions. Both tests provided satisfactory results, and the 10 hot firings were scheduled. The broad objective of the hot firing program was to define and evaluate requirements for in-space start, shutdown, and restart. One objective of the testing was to refine the pre-flight countdown for launching. Refinements will be incorporated into the flight countdown. Of major interest was the capability of advanced propellant utilization, a system for sensing and controlling the levels of liquid oxygen and liquid hydrogen in the tanks. An optimum system will control the ratio of the 2 propellants so that they deplete at the same time, calculated to occur at the optimum time for engine cutoff.
Engine cut off.
The first 4 firings were aborted before full tests could be completed. They uncovered a number of problems, including faulty chamber pressures, a turbine bearing temperature too low for good performance, a hydrogen leak at the boost pump, and an overpressure in one of the diffusers. In the 4th countdown, engines fired for 2 1/4 seconds. After the cutoff, an examination of the C2 thrust chamber revealed a defect. 2 small holes burned in during the brief firing. Tests were suspended until the engine could be replaced. First run of the planned series of 10 was accomplished December 17th. All systems operated successfully with an engine firing duration of 30 seconds. Subsequent run times will increase until full duration is reached, with cutoff and restart as programmed for the 2-burn Centaur. Centaur is under the direction of NASA's Lewis Research Center, Cleveland, Ohio. Lewis engineers provide special support for the program, which can best be accomplished at the advanced facilities available at the research center. One of these support activities utilized NASA's Space Power Chamber for altitude tests of the balanced vent system. The facility simulates altitudes up to 100,000 feet, subjecting the vent system to conditions close to space operation. Early tests measured net thrust and the flow rate and pressures at the exit nozzles using helium gas. Data from these provide support for more advanced testing at cryogenic temperatures. The test series started at sea level pressures to simulate ground venting. A mid-range test simulated vent operation between 35,000 and 40,000 feet. Advanced testing simulated altitudes between 90,000 and 100,000 feet, closely approximating the conditions of coast phase flight. In another area at Lewis, a series of tests investigated the effect of propellant slushing in the Atlas fuel tank under abnormal amplitude conditions. For these, a quarter-scale Atlas fuel tank was mounted onto the NASA experimental slush force test bed. Test sequencing simulated slush amplitudes, which have an adverse effect on launch vehicle stability. In one series, the tank shear membrane was in place. The second series of tests investigated slush characteristics within the tank with the shear membrane removed. Results from the 2 series will be compared to ascertain the effect of this membrane on slush motion. The evaluation will lead to a more precise definition of the vehicle's stability margin. With most of Centaur's systems proven, research and development for the project centers upon product improvement or refinement of data. Convair's environmental test laboratories play a key role in this continuing task. For example, in one project, a technician subjected samples of Teflon to thermal shock. This material is used as a seal in the liquid oxygen vent duct on AC-8. A total of 24 samples went through the cycling process. 12 of them, varying in thickness from 2 to 20 mils, were control samples, not subjected to thermal shock. An identical 12 were cycled in and out of liquid nitrogen 200 times, exposed 5 seconds to a temperature of minus 320 degrees, and 10 seconds to room temperature. A weight at the bottom of the sample loaded it to 780 pounds per square inch. Objective of the dip tests was to determine the effect of thermal shock on the tensile strength of the material. After dipping, samples were tested to destruction in another lab. Variables were elongation of the samples and the force required to break them. For 20 mil samples, there was no significant difference between those subjected to thermal shock and the control samples. Thermal shock had little or no effect upon the tensile strength. For thinner samples, data produced surprising results. Thermal shock samples proved to be stronger than control samples. A possible explanation of this phenomenon is that the Teflon, under constant load thermal shock, undergoes a uniaxial alignment of its molecules. The actual mechanism which causes the increased strength could be established by tests such as X-ray diffraction or measurement of optical characteristics. In another study, engineering began a detailed study on characteristics of flexible linear-shaped charges at different temperatures. In this case, the shaped charge is a V-shaped strip of metallic sheath explosive used to cut loose flight hardware for jettisoning. When detonated, the explosive force travels vertically from the flat inside surfaces. At the point of intersection, the forces redirect themselves into a cutting edge which knifes through the material at a 45-degree angle from the initial direction of force. The material for the tests was a metal plate grooved to produce a sample providing metal thickness over a wide range in the one sample. The charge, which duplicates flight hardware, is encased in a strip of laminated fiberglass, spaced to provide the required distance from material to be cut. The strip which houses the charge mounts to the flat side of the test sample. A series of tests provided data on samples exploded at room temperature and at cryogenic temperatures. For cryogenic tests, plate and charge are installed into a double-jacketed cylindrical container. Liquid nitrogen flows through the outer jacket. Liquid hydrogen, at minus 423 degrees, flows through a cooling tube, which is in contact with the plate of the specimen, cooling it to about minus 400 degrees. When the sample reaches the proper test temperature, the charge is detonated and instrumentation records the results, primarily the time intervals at various points along the charge. The sample is examined for depth of the cut, then compared with previous samples for consistency. To date, there has been no significant difference noted between tests at different temperatures. Using the same apparatus, tests have been run to determine the ability of the charge to jump gaps in the test specimen. This test fixture is an air-bearing device used for simulating the separation of Surveyor from Centaur. The simulated Surveyor is suspended from an overhead frame supported on knife edges mounted to the retromotor. The complete assembly slides on nearly frictionless air bearings. Surveyor attaches to a Centaur adapter which includes an electrical disconnect mechanism, separation latches, a switch that senses an inadvertent separation, and the springs which push the spacecraft free of the booster in space. Tests were initiated by a laboratory programmer. Instrumentation measured axial acceleration, pitch and yaw movements, and precise timing of events. The main variable used for these tests was a programmed relocation of the center of gravity between operations. Results of tests at this stand verified the proper functioning of separation components. At the end of 1965, operational Centaur AC-7 was on standby at Complex 36A, Cape Kennedy, Florida. AC-8, a two-burn research and development vehicle, was in final stages of assembly at Convair. It was scheduled for shipment to Cape Kennedy in January. Also in final assembly was AC-9, the second of two Centaurs that will fly a two-burn research and development mission. AC-10 is a single-burn operational launch vehicle. It is an advanced vehicle with improvements in guidance. The additional ground testing required for the SC-1 Surveyor vehicle has resulted in a rescheduling of the first operational Surveyor flight. As a result, Lewis Research Center directed Convair late in this report period to return AC-7 to San Diego for updating and to combine SC-1 with AC-10 for CSTS operations and the subsequent launch. Of the remaining Centaur vehicles under contract, all 5 were in production in various stages of fabrication. AC-11 will fly a one-burn direct descent operational mission. Beginning with AC-12, all subsequent vehicles will fly two-burn missions. In the year ahead, the major emphasis for Centaur will be on manufacturing, acceptance testing, and flight. and studies involving advanced applications. In 1966, Centaur will become a fully operational space vehicle for both the single-burn and two-burn missions. During the year ahead, a surveyor spacecraft will land on the moon to transmit our first close-up views of the lunar landscape.